Modern data processing requires coordinating thousands of servers to analyze massive volumes of information simultaneously. Scale and speed are the primary objectives. The bedrock supporting this massive scale is the Hadoop Distributed File System, or HDFS. It distributes exabytes of data across vast server clusters to be processed in parallel. This diagram illustrates a classic HDFS topology. Despite the massive array of gray data nodes at the bottom, the entire hierarchy funnels up to a single central manager, the NameNode. The NameNode manages the file system namespace and metadata. When a client requests a file, the NameNode consults its internal directory and points the client to the exact physical data nodes holding those specific blocks of data. If a hardware failure or a kernel panic occurs specifically on this central NameNode, the metadata disappears. The underlying data still exists on the healthy data nodes. Petabytes of intact information sit on fully operational hardware, but without the NameNode's directory to locate it, the entire cluster is logically inaccessible. In systems engineering, this architectural flaw is known as a single point of failure, or SPOF. In partnership with the data engineering team at Royal Research, we are going to systematically re-architect this system from first principles. Our goal is to achieve true high availability. Deploying 10,000 data nodes offers no resilience if the system's brain remains a single point of failure. Scaling a distributed system safely requires eliminating the SPOF at the metadata layer. The initial engineering response to a single point of failure is physical hardware redundancy. We duplicate the critical component. Returning to our diagram, we deploy two identical NameNodes side by side, Active and Standby. Under normal conditions, client requests route exclusively to the active node, while the standby remains disconnected, sitting idle. Every time a file changes, the active node generates an edit log, a continuous record of metadata changes. This creates a gap. The active node stores logs internally, but the standby receives none, lacking visibility into the evolving cluster. If the active node dies now, the standby possesses an outdated map of the file system. Promoting it to active status would result in metadata inconsistencies and potential data corruption. Unlike a stateless web server, a distributed file system manager must maintain an accurate record of every file location across thousands of machines. In stateful systems, hardware redundancy without continuous state synchronization is insufficient. It is merely a delayed failure. We need a mechanism to bridge this state gap. The architecture requires a highly available shared storage layer situated between the two nodes. This chart shows the introduction of JournalNodes. This separate cluster of components acts as the shared storage for the NameNodes. JournalNodes are deployed in a quorum of 3 or more for fault tolerance. The active NameNode continuously pushes its edit logs to them, while the standby pulls those identical logs into its own memory. We have achieved state mirroring. The standby node now maintains a real-time exact duplicate of the active namespace. If the active node crashes, the standby has already processed the exact same metadata transactions. It can take command of the cluster immediately. By decoupling the storage state from the computing node and placing it in a JournalNode quorum, we transform passive redundancy into active readiness. We have solved the metadata synchronization problem, but we must now address a more dangerous failure vector than a standard hardware crash, the network partition. If a network switch fails, the active node might lose its connection to the network while remaining internally healthy. It will continue to operate as if it is still the cluster master. Detecting network silence, the standby assumes the active node failed and promotes itself. Now both NameNodes are active, writing conflicting updates. This is split brain, resulting in immediate data corruption. The architecture requires an independent external arbiter to maintain consensus and determine which node is the true master during a network failure. This is the role of Apache Zookeeper. It is a centralized coordination service that provides distributed synchronization and configuration management. Zookeeper establishes a continuous health monitoring system. It maintains active sessions with both NameNodes via rhythmic network pulses to verify their reachability. If the active node becomes unreachable, Zookeeper coordinates failover. It executes fencing, revoking the old node's write access to the JournalNodes, isolating it. Only then does the standby assume the active role. Preventing data corruption is more important than uptime. High availability requires an automated arbiter to enforce consensus and strip compromised nodes of their power. While NameNode High Availability solves the metadata bottleneck, it does not protect against physical catastrophes like a regional power outage or a facility fire. To address this, we implement multi-data center deployment. By replicating data and services across geographically distributed locations, a failure in one data center does not disrupt the entire system. To mitigate network-related issues, we implement hardware redundancy through multiple network paths and load balancing. This ensures continuous connectivity between cluster components. For data durability, HDFS supports data replication and erasure coding. These mechanisms store redundant data blocks across multiple nodes to protect against hardware failure. Managing the interplay of Zookeeper, JournalNodes, and distributed hardware requires constant visibility into the cluster's health. Tools like Apache Ambari and Cloudera Manager provide real-time dashboards for monitoring Hadoop components, allowing for the quick detection of performance issues. Automated failover is not a substitute for regular backups and a robust disaster recovery plan. These measures ensure data can be restored following catastrophic failures. We started with a configuration dependent on a single isolated directory. By introducing JournalNodes to decouple storage state and integrating Apache Zookeeper to automate consensus, we have developed a fault-tolerant distributed system. High availability is a layered philosophy, from metadata synchronization to macro-geographic redundancy. Thank the engineering team at Royal Research for their partnership in this technical breakdown.